One of the things that we deal with right triangles is that obviously you have to have a right angle.
Oh my gosh.
Correct. So now when you start going through your right triangle, then you can start labeling parts of the triangle. If you know you have a right triangle, you know that you have a right angle, which means you know specifically where one part of the triangle is located. Which part is that? The hypotenuse. The hypotenuse will always be opposite your right angle. Always, always, always. Okay? The other two parts were called legs. Yes, sir?
I had an idea for a joke, but I'm not sure if it's going to be that funny.
Well, then we'll hold on to it. The other two parts were called legs. It was either an opposite or an adjacent, and it just depended upon placement of the angle. Remember, trigonometry is all about perspective. It's all about where you are in the location. So I'm going to place theta, which is a symbol for angle, that we use in Algebra 2, there. You are always, always looking at your opposite. Your angle always opens up to the opposite, which means by process of elimination, this has to be your. Why isn't the hypotenuse your adjacent? Because it's the hypotenuse. The hypotenuse supersedes adjacency. Hypotenuse is more direct than an adjacent. It's a more specific value. Okay? So it takes over. I know you guys know all of that. I know you remember all of that. You should. You also remember a little bit of something called SOHCAHTOA. The chief, the proud Indian tribe.
Are we going to walk around and chant it again?
What did it stand for again?
Opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite adjacent.
So you guys would use right triangle trigonometry to solve for missing side lengths, solve for missing angles, things like that. For example, just for fun, how do you spell hypotenuse? H-Y-P. Fine, thanks. You? Good. What trig function are you going to use to solve for that?
Wait, what is
Wait, it's
sine.
Never mind.
Remember, you start always at your angle to know your location. Draw what's across from you, so that's your opposite. And this has to be the hypotenuse. So you have the sine of 17 is 3 over x. If you recall from last year, there was a really, really, really nice trick to solving this when you had the unknown value in the denominator. Do you remember? Okay, well, let me ask if you remember this. True or false?
True.
Okay. True or false? What'd I do? So if I put sine of 17 over 1, bless you, does it change anything?
No.
No, which means the shortcut was to do this. Okay. Whenever your unknown variable was in the denominator, when you're using sine, bless you, we would just switch them on the diagonal. It was the shortcut. Okay?
Wait, can you go up a little bit?
Not a dumb question. It's the idea that you're located at this angle, and then you label your parts. You have your opposite, and you have your hypotenuse. You're trying to find the opposite. Or excuse me, the hypotenuse. And then you just go through the SOHCAHTOA to figure out which one to use. Okay. So that was the kind of thing that you did. You also, at some point in time, had to solve for an angle, I believe. And in this case here, if I wanted to solve for my angle, I have the two sides, the 5 and the 17. I would use tangent. Very good. So in order to solve for that, you'd have to press some buttons on your calculator. You knew that the tangent of theta is your opposite over adjacent, but you had to remember how to solve for the angle. You had to use the arctan, or the tangent to the inverse, the -1. Remember that button? Yeah. Now, on these calculators, what we need to make sure, first of all, is that we are in degree mode. You know how to check that. Ms. Bella? Theta. It's like an angle. It's just x. Instead of x, I'm using theta. This is the Greek symbol for theta. Yeah, but you have to have special angles. So you'd have to take the inverse tangent of both sides. So your theta value would be the inverse tangent of 5 divided by 17. Now, did you guys know how to check your mode in the calculator? No. All right, hit the button that says mode, convenient. And you want to make sure that you're highlighted in degree. When we switch to radians, it will no longer be rad to use the calculator. Okay. Rad, radians, RAD.
Wait. Sorry.
What are you guys getting for your angle measure here?
16.389.
389, so it's 16.39 degrees. Okay. Well, I don't know. It just went to the first person, so I probably should do that. Oh, someone's tough.
I got 17.
Wait, is that 5 over?
17. 16.39.
What did I do wrong?
Bam.
Math. Yes, ma'am.
Wait, can you help me with this calculator?
Yes.
So like I pressed that one.
Yeah, sir. It's built off the unit circle. Yes, sir.
I like.
So I'm finding the angle. I'm not finding the angle. I'm not finding the side. Okay. All right. Now the other thing that you guys did. Were your special triangles? You had your two special right triangles. You had the 30, 60, 90. And the 45, 45, 90. Now I know that Seb did this a little bit differently than I did. Seb used the P's and Q's. No, I set it up a little bit differently. I used the well, that's I use X. Okay. And there's a reason why we use an X, and I'll show you guys that here in a little bit. Remember, we set it up with 45, 45, 90 right triangles are an isosceles right triangle. Every single isosceles right triangle will always measure 45 degrees for the base angles. Okay? And what happens here is that depending upon what we have, there's always going to be some sort of factor, like a scale factor being multiplied through. That's where this value of x, bless you, this is where this value of x comes into play. What's the coefficient of x in this problem? 1. So basically what we're setting up here is that if this side is 1, this side has to be 1. Well, what's 1 squared plus 1 squared?
1,
2. And what's the square root of 2?
2 root of 2.
So that's where you get those side lengths of 1, 1, and root 2. This value of x is the scalar multiplier of all this. Now, in these types of problems, they were quick problems, ones that you would use non-calculator. For example, if you were given across from the 45-degree angle and you knew that this one was 7, what's across from the other 45 angle? 7. And what's across from the 90? 7 root 2, okay? Now, what if you were given across from the 90 and it was 10?
Then you divide.
Very good. Then you divide it by the square root of 2. Very. And that what came into play with this is that if you were given across from a specific value, you'd have a one-step equation to solve. Yes, ma'am.
If you want to start
No, it's fine. You believe me, we probably won't be using a lot of this. It's just going to fall into 1, 1, or 2 here real quick. Okay. Yes, sir.
You only use root 2 for right?
Yes, sir. Okay. So if this equaled 10, it was a one-step equation. You divide both sides by. Remember the trick? You had to rationalize it. Yes, sir.
You multiply over 1, so root 2 over root 2.
Correct. You multiply by that. There was a shortcut though. Anytime you rationalize your denominator with the root 2, cut the numerator in half, slap a root 2 next to it. So it's 5 root 2. So your value of x here is 5 root 2. So what you're doing is you're figuring out that scalar. 5 root 2 times the square root of 2 is 10. That's where that came from. Same deal with 30, 60, 90. 30, 60, 90 was built out of what kind of a triangle?
Scaling, right.
Yes, I know it's a scaling right triangle. Thank you. It was built out of an equilateral triangle.
It is a scaling, hey, I was right.
That's not equivalent.
It was built out of an equilateral triangle because you drew the altitude of an equilateral triangle, which created a perpendicular bisector, which created 30, 60, and 90.
Oh, I don't
Wait,
know.
what's that line?
The altitude. Equilateral triangle, you guys agree?
Yes. Yeah, I remember that.
Draw the altitude in, it becomes 90.
Yeah.
Equilateral has a 60 here, therefore 60 plus 90 leaves you, 30.
30.
The altitude of an equilateral triangle was the perpendicular bisector of the base. So, if this was 2, this is a 1, this is a 1, and this is a root 3.
Always said.
Okay. So, going back to this, we wrote it out in specific patterns. You had an x root 3, and a 2x. Yeah, it comes back real quick. You'd be surprised. X root 3. Okay. And real fast, I wrote it up. I started using it on the back wall because it was helping some people earlier. Is that I just started writing them out as 1s and root 2s, 1 root 3s and 2s, because eventually, what we're going to wind up doing is taking the special right triangles, and we're going to create the unit circle via it. Because the unit circle is only made up of 3 different angles. It doesn't. Do you know a 30, 60, 90, and a 45, 45, 90? Then you're fine. Here's your 30. Here's your 45. Here's your 60. Now, if I'm looking at this in terms of 1s and root 2s and things like that, let me show you. Might as well do this real quick. If I want to find the sine of 30, cosine 30, tangent, oh, you know what? Let's just do this. Let's make this. Let's make it blow this up a little bit better. And I'm going to talk about these inverse functions here in 1 second. All done. Sine, cosine, tangent. Now, cosecant, secant, and cotangent, I'll talk about those in a second. Those are the inverse trig functions, reciprocal identities. And I'll explain that in a second. Yeah, I would. Because this is this right here is the basics of everything that you're going to do, aside from a little bit of things. The majority of the things you're going to do over the course of the next month and a half is built out of this chart. Yes, ma'am. Oh, it's just theta, just your angle. It's just some angle. Okay. What happens here is you get these 3 different angles, 30s, 60s, and 45s. And what those do is they create ordered pairs along our unit circle. Now, what we do here is that each ordered pair has a specific endpoint, because within a circle, isn't the radius always the same? So this radius here, for each of these, is the same, coming up and around. If I give the radius of 1, this ordered pair here at 0, if you will, is going to be horizontally 1, vertically 0. That makes sense? Now, look at when I draw a 30-degree in, it creates a right triangle if I go horizontal and vertical. Are we okay with that? So this would be my opposite, the vertical. This is my adjacent, the horizontal. What's the sine of 30 degrees via your special right triangle? Well, in a special right triangle, your 30-degree opposite it is a 1. The hypotenuse is the 2. And the opposite the 60 would be the root 3. What would the sine be then? Opposite over hypotenuse. 1/2. The sine of 30 is 1/2. It's opposite over hypotenuse. What would the cosine of 30 be? Cosine, adjacent hypotenuse. So your sine is opposite over hypotenuse. Cosine is your adjacent over hypotenuse. So your cosine of 30 is adjacent hypotenuse. Okay. What's your tangent?
Opposite over adjacent.
Opposite over adjacent. So your tangent is opposite over adjacent. So that would be 1 over root 3. But we don't leave it like that. How do you rewrite it? No. What is it? Someone said it.
Root 3 over 3.
Good. It's root 3 over 3. You rationalize. Multiply top and bottom by the root 3. That's where you get your root 3 over 3. Okay. Now, before we get into the 60s, let me explain to you guys what these next 3 are. The next 3 are what you call the reciprocal properties.
Someone at the door. We have on.
So you have cosecants. What's up, Stephen?
0 and 5. All right, thanks.
All right, buddy. Your cosecant of an angle is the inverse of a sine of an angle. Cosecant and sine are inverse functions of one another. Okay, they're inverses of one another. So, and then this, you can write it like this as well. Sine is 1 over cosecant. Notice I did that on the diagonal again. So you can see it right there. So if sine is opposite over hypotenuse, what do you think the inverse of that for cosecant would be? It's your hypotenuse over opposite. It's the inverse of 1/2, which is 2 over 1. Okay. Secant is the inverse of cosine. So secant of theta is 1 over cosine, or cosine of theta is 1 over secant. So if cosine is adjacent over hypotenuse, what's secant? Hypotenuse over adjacent. So instead of trying to relook at my root 3 over 2, if I'm doing secant of 30, it's going to be 2 over root 3, hypotenuse over adjacent. But I can't leave it like that, can I? Very good. 2 root 3 over 3. And And then last but not least, cotangent. What do you think cotangent is going to be the inverse of? Tangent. And then cotangent is the inverse of tangent. And tangent is the inverse of cotangent. So if tangent is opposite over adjacent, cotangent will be? Correct. It's just root 3 over 1. I just leave it as root 3. Okay. Let's go through that again with the 60s. What would the sine of 60 be? Root 3 over 2. Change colors. Cosine. 1/2. Tangent. Root 3. And now you just do the reciprocals. What's the reciprocal of root 3 over 2? 2 root 3 over 3, very good. What's the reciprocal of 1/2? 2. And the reciprocal of root 3? Notice how they're just shifted over a little bit? The values wind up being the same because they're still within the same triangle. They're eerily similar. This is what allows you to sit there and say, okay, if I have a horizontal distance, that's my adjacent value. So that means I'm looking at the cosine. Well, what was the cosine of 30 degrees? Cosine of 30 degrees was root 3 over 2. What was the vertical of that? Well, the vertical of that you found by sine, 1/2. That gives you an ordered pair for the endpoint for a 30-degree angle. That 30-degree angle can be replicated within all 4 quadrants within that unit circle. Each one of them will have what will eventually be called a reference angle of 30 degrees, bouncing off the x-axis 30 degrees. Eventually we'll call that pi over 6. This ordered pair, moving horizontally, just changes the x value. Because as you go to the second quadrant, the signs, S-I-G-N, go negative, positive. As you go to the third quadrant, what do your signs become? Negative, negative, which means this ordered pair, since it just went vertical, the x value didn't change, the y value just shifted. So you have negative root 3 over 2 and negative 1/2. You come back over here, the x value all of a sudden is positive again, but your y value is still negative. So these values, this, what we're looking at here with this table, is going to be the basics of everything we do in about a week and a half. Okay? Everything we need to know is built into 2 triangles, 3 different angles. Okay? Comes out of 3 angles. 45s. 1, 1, root 2. We okay with that? Instead of using x's? It's nice that your sine and cosine values are identical for these. 2 root 2 over 2. Are we okay with that? So it'd be 1 over root 2. So you have root 2 over 2. Root 2 over 2. Which gives you a tangent of 1. Which gives you a cotangent of 1. Inverse of tangent is cotangent. Cotangent would be adjacent over opposite. Well, it's still going to be 1 over 1. All right. When I go to do the cosecant and secant, hypotenuse over opposite, root 2 over 1. Root 2 over 1. Okay. This is why at the ordered pairs of at 45 degrees, you have the same value for your x and your y. Because your ordered pairs go, what comes first in the ordered pair? X value, because it's first in the alphabet, right? What comes first in the alphabet, cosine or sine? So which one do you think these represents cosine, which one represents sine? That's your cosine, that's your sine, going all the way around.
Beautiful circle.
Thank you. And it's all built out of these two triangles. Trig is awesome. Okay? And then you'll notice as your cosine value starts high, works its way down, gets negative, and it comes back up, because your cosine graph does that within one revolution. Your sine graph starts at 0 and works its way up and back down.
That's
Yep.
DNA.
Yes, sir.
how can we use this in like
Sinusoidal models. Anything that has anything that has a periodicity to it, anything that's replicated over that has the same period wavelength stuff. Light waves, sound waves. Sound waves not so much because they think they disperse after time. But light waves, measuring distances, you can do all this stuff with it. Trigonometry is one of the most practical things you can use. Okay. Yes, sir.
So we are going to be graphing these?
Oh yeah. We graph sines, cosines, tangents. This year I'm doing something new with you guys. I'm going to have you guys graphing the inverse functions as well. It's actually pretty simple. Okay? It's kind of cool. Wait till you see the pictures. They look awesome. Okay. Yeah, we did this one. Real quick because we're going to run out of time here. Do you remember angles of elevation versus angles of depression? No trig lab. Manometers, protractors, all that stuff.
I hated those. So fun.
So you are in a lighthouse, 350 feet up, and see two ships at sea.
I'm afraid of heights. I don't ever think I would be that high. I can't.
Ah, where your friend is.
Wait.
One has an angle of depression equal to 4 degrees. The other one has an angle of depression equal to 6.5 degrees. How far apart are the ships? Well, if you remember the thing that you did last year with the clinometer stuff, it's a very easy thing to use. Knowing a specific, if you know one height and an angle, you can measure distances all the time. That's what's cool about trig. When you see people out there with the surveyors, they're looking through the scope stuff, the guys out there with the peg and they're trying to measure stuff out, that's what they're doing. If you ever use a rangefinder, what it's doing is you're trying to calculate a line of sight distance to figure out elevation changes and all that kind of stuff. You can do all that. So if you think about being up at a lighthouse, well, you need to draw a lighthouse. On the very top of the lighthouse is a giant flashlight.
Cute.
That's beautiful.
Lighthouses have stripes.
And they're red. They're red. Oh, that was a good thing.
Wait, you got on
It is a candy cane.
Okay?
Where's the door?
No, it's kind of equal.
It's a
There's
massive
usually
candy
water
cane.
by the lighthouse.
Don't forget the rock.
It's a very calm day at sea.
But there's ships in the water, so it's
Yeah.
really not.
So then there's a couple of boats out here.
They're actually
Why can't I
ships.
see through the water?
Very true.
Is that the
Can you draw a
email?
really big one?
But so, are you looking at the angle though?
Yes.
I can draw
They're
And
round.
then it's
big
just a
sail.
round.
It's a bigger boat this far away,
Who's that?
and this guy has a water skier.
How does that
Actually drawing.
So that guy's water skiing.
What about the Titanic? It should be at the bottom of the ocean.
So, angle of depression. Angle of depression is line of sight looking down. Line of sight is always going to be parallel to the ground. When you're looking off parallel downward, this is the angle that you're talking about. Line of sight down is the angle you're looking down towards something. Now, two parallel lines cut by a transversal states that alternate interior angles are congruent, equal. So if this is the angle of depression, this would be the angle of elevation. Angles of angles of elevation and angles of depression are congruent. The one thing you got to remember is that a depression angle does not drop into the triangle. The depression angle is the line of sight down. You want to slide down to look back up. Okay. So if you have one of them here and the other one is here, what you need to figure out is which angle goes where. Well, if one angle is 4 degrees, the other one is 6.5. Which one goes to the further away boat?
4.
4.
It's small.
The smaller angle. Okay. The 4 would have to go here, which means this would have to be your 6.5. What is, if you know that, that means this angle here is 6.5, and this angle here is 4. What is the side length that you know? The 350 of the lighthouse. It is the what in relationship to the angles? The opposites. We know that this height here is 350 feet. Now, if I want to figure out how far apart the boats are, I need to figure out, first of all, how far they're away from the lighthouse. So I need to figure out this distance from here to here, which would be the adjacent. And then the other one would be the other adjacent, because there's two triangles. Now here's where it gets goofy. Give up. If this is 8 and this whole thing is 10, what is this? What did you do?
Math.
He did algebra.
There's no way that he's 8 feet away from the coast.
This is really dangerous.
So in order to figure out how far apart they are,
You guessed it.
guys, in order for us to figure out how far apart they are, we have to take their two separate distances and subtract them. So what trig function are you going to use to find the adjacent for the first boat?
Tangent.
Good, tangent. So we have the tangent of 6.5 is your opposite, 350, over your unknown. What trig function are you use to find your adjacent for the second boat? I'll use that for y. Remember, utilize the idea that there's only two ways to solve trig equations. If you're taking the if you have the angle measure, your unknown variable is going to be either in the numerator or denominator every time. The trig, whatever the trig button is, can change. But if I have the variable in the bottom each time, all I do is switch it with the trig function. Each and every time, always works. So, excuse me, the two angle or answer will be x will be 350 divided by the tangent of 6.5. This would be 350 divided by the tangent of 4. And I heard someone start saying this is what, 3,000.23, I think? 84? Okay. The other one's 0.23.
Yeah.
5,005. Yeah, you know, you have to take it with a grain of salt. It's really not drawn to scale, sorry. So how far apart are the boats?
2,000.
Would imagine be less than 2,000.
My estimate is 1,933.32 feet.
So these two boats are 1,933 something feet.
They're about 2.
Well, it's possible. Not drawn to scale. That's your angle of elevation, angle of depression stuff that I know you guys have all done. It's just been a while since you've done it.
It is fair.
Okay.
I did.
Well,
just
like I
did
said,
it well.
one of the things I like to do in 13, in this start here. Yes, ma'am. Yes. This is right. Yes, this is assumed it's a right triangle. Yes. Okay. We will use sine and cosine with non-right triangles. That's with law of sines, law of cosine. But right triangle trig is SOHCAHTOA. This is what we're doing here. Okay. Now, like I was saying, with this stuff here, I tend to just kind of give you guys problems and just start. Okay. It usually takes about a day and a half for you guys to remember how to do trig, and then we'll build out of it. So come towards the end of the day on Wednesday, or maybe even tomorrow, depends how well you guys are going. We'll probably start law of sines, law of cosines tomorrow afternoon, Wednesday, and then that'll get us into working in the ambiguous cases, and that usually takes a little bit of time. But there's a really cool shortcut that I'll show you guys to make them work. Okay? Let me give you some props. Or do you want?
problems, that's okay. What does that mean?
What?
Literally almost.
Symbolize something?
He was killing time.
We shouldn't kill anything.
You're right. I should have drawn in a narwhal.
That denotes violence.
Yes.
You can't say that.
Well, I drew in a I did this earlier, and I drew a narwhal in there because my kids were watching Elf yesterday. Hello, Mr. Narwhal. What's that?
I really think it's just because you missed my little drawings that I used to put on my homework assignments.
Yes.
Right, Bird Dog?
Sure.
Oh.
Yeah,